In previous videos, we learned about the difference between accuracy and precision, and then we learned about significant figures, which is a tool for reporting precision. Now, scientists rarely just write numbers down and leave them there. Most of the time, we do arithmetic of some kind when we build our models and use our models. So we need to have a way to deal with the arithmetic that happens when we have measurement data and keep our precision correctly reported. So this video is about doing arithmetic with numbers where precision counts. How do we do arithmetic with significant figures? The goal here is to make sure that we don't over-report or under-report the precision as we start to add, subtract, multiply, and divide numbers as we use them in our scientific models. Let's learn about adding by taking a look at a case. Let's imagine that the length of a field in a park was originally decided by having someone just pace off 70 meters. So this person paces off 70 meters, and they happen to know that their precision, because they've tested it out maybe, is plus or minus 1 meter when they measure by pacing. So they would write that the way we have it here, 70 with a decimal point after it. And what that's saying is we know that the precision is, we know for sure the tens place, and this is our variability. So this number could be as high as 71, it could be as low as 69. That's the precision that they have by pacing. Now let's say some workers come along and they're going to make the size of this field shorter because they have to move the fence. So they are not just pacing, they have a tape measure. So they measure the distance between where the new fence is and where the old fence was, and they have the ability to read here much more precisely. Here they have 7 meters, and then these markings are tenths of a meter, and so then they can actually estimate within that and read this to the nearest hundredth of a meter. So they measure the distance that they've moved the fence, and it's 7.34 meters, and they write it as 7.34 because they know the meters for sure, they know the tenths of a meter for sure, and their variability, their estimate, comes at that 0.01 meter decimal place. So what's the new length of the field? Well, you might think we can just take 70 meters and subtract 7.34 meters, and we come up with 62.66 meters. Is it appropriate to write that measurement that way? Well, to answer that question, let's think about what 62.66 meters means when we're thinking about significant figures. The largest this number could be is 62.67, and the smallest it could possibly be is 62.65, because when you write this way, taking into account significant figures, that last digit is an estimate and it floats plus or minus 1. So 1 bigger than 62.66 to 1 less than 62.66, that's the range of what the measurement actually is. What's the length of the new field? But now we have to consider that the two numbers that went into this don't have the same precision. Remember, the original fence was placed at 70 meters, but that was only plus or minus a meter. So if the person who paced that off was a little bit high that day, then actually it was 71 meters minus 7.34 meters. And so the new length of the field would be, in that case, 63.66 meters. But it could also have been the case that that person was measuring just a little bit low that day. So if that was the case, then it would have been 69 meters, or closer to 69 meters. And if you subtract your 7.34 meters from that, the length of the field now is 61.66 meters. So here's our new range. If we consider the fact that we only had plus or minus 1 meter in our original measurements, the maximum could be 63.66 and the minimum could be 61.66. If we look at the maximum and minimum that we had when we considered the precision of the tape measure measurement, this whole entire range is way, way smaller than this range. So if we wrote down a number that's 62.66, that is actually not appropriate because that overstates our precision. We really only know it plus or minus a meter, but we were telling people we knew it plus or minus 1/100th of a meter. So this gives us a rule. When adding measurements, round to the last decimal place in the least precise of the measurements. So in this example, we had less precision there with the 70 meters, more precision with the 7.34 meters. The less precise number was good to the nearest 1 meter. The more precise number was good to the nearest 100th of a meter. So we would round to what's less precise, and that's the nearest meter. So rounding 62.66 to the nearest meter gives us 63 meters. By the way, subtracting, which is what we did here, is just adding a negative number. So adding and subtracting have the same rule because they're the same arithmetic operation. Now let's take a look at multiplying measurements. This is a little bit harder. So here's an example. Several lengths and widths of an object were measured, and they were measured with a tool that has two significant figures. All these measurements for length and all these measurements for width have two significant figures. They're good to the nearest tenth. When you multiply them together to get the area, these are the results that your calculator tells you. Now, what do we know about these numbers? If we look at them, we know that every one of them starts with a 4. So in the ones place, all of them are 4. In the tenths place, there's variability. 4.5, 4.7, 4.7, 4.5, 4.7. It doesn't make any sense to round our number to anything more precise than the nearest tenth because we already know that when we get to the tenths value, we have deviation. So it makes sense to round to 4 point something, and that gives us two significant figures. So what we found was when we measured a number that had two significant figures by a number that had two significant figures, we get an answer that we should round off to two significant figures. Let's look at another example. This time the length and width was measured with a more precise tool. So we're good to the nearest 100th here, and that gives us three significant figures. Same thing with the width, three significant figures. Now let's look at the area values that are calculated. What we notice is all of the ones place are the same. It's always a 4. Now we notice that all of the tenths places are the same. It's always a 5. It's when we get to the hundredths place that we start getting variability. 4.55, 4.59, 4.57, 4.58. So it doesn't make sense to round to the nearest 1 or the nearest tenth because those numbers are all the same. It doesn't make sense to round to the nearest thousandth because we already are seeing variability when we get to the nearest hundredth. So these calculations should be rounded to 4.5 something, and that would give us three significant figures. So what do we see here? When we started out with three significant figures and we multiplied by a number with three significant figures, we have a number that should be rounded to three significant figures. Let's look at one more case. Here we have the lengths measured with a tool that gives us two significant figures. And the widths are measured with a more precise tool that can give us three significant figures. When we multiply them together to get the areas, what we notice about the area values is all the ones place digits are the same. They're all 4s. But we get variability when we get to the tenth, just like we did in our first example. 4.4, 4.6, 4.6, 4.6, 4.6, 4.4. So that's where we see our natural variability come up in our answers. So it doesn't make any sense for us to round to the nearest hundredth because we already know that we have variability in the tenths value. So we should round these measurements off to 4 point something, and that would be two significant figures. So we see that when we multiply a number that has two significant figures by a number with three significant figures, we should round off to two significant figures. So this gives us a rule. When you're multiplying measurements, round the answer so that it has the same number of significant figures as the least precise of the measurements. So how this is like our rule for adding is we're still going by the least precise measurement. We don't want to overstate our precision. But this time, instead of going by decimal places, we're going by significant figures. Example, if we were to take 5 meters and multiply by 6.501 meters, our calculator would tell us 32.505 square meters is the area that we would get. Now let's look at precision. There's one significant figure in 5. There are 4 significant figures in 6.501. The least precise of these by significant figures is the 5. And so that means our answer should be rounded also to one significant figure. And if you round 32.505 to one significant figure, the 2 rounds us down to a 3 in the tens place, and that's just 30 square meters. And by the way, dividing is just multiplying by a number that's smaller than 1, so the same rule would apply for dividing as it does for multiplying. So now we have the ability to use arithmetic with our measurements without overstating or understating our precision by following a couple simple rules. Let's just recap what the rules are. When you're multiplying measurements by each other, and dividing is the same as multiplying, you round the answer so that it has the same number of significant figures as the least precise of the measurements. In other words, that's the one that would have the fewest significant figures. When you're adding or subtracting, you round the answer to the least precise of the 2 measurements, but you go by decimal places instead of significant figures.